Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
So in this lecture, we are going to see how to design reinforced concrete structures against fire. So we have already seen how fire can be characterized as a load, how temperature calculations can be done for steel as well as for concrete structures. For steel, we use the lumped capacity approximation or model, and for concrete, which is an insulating material, we use the semi-infinite boundary condition approximation. We also saw this Wickstrom's method for temperature calculations for concrete or masonry type structures which are thermally insulating. Okay. And then we also have seen how to design steel structures under fire, and we noticed that for steel structures, unprotected members are highly vulnerable to the effects of fire, adverse effects of fire. Hence, most steel structures needs to be provided with fire protection of appropriate level to ensure their performance under fire. We will do a quick review of the design philosophy. You may recall that we can define a limit state function, okay, for limit state method of design, and we defined one under fire conditions, which is this L fire. Okay, it is a function of D fire, which is the demand under fire conditions, and R fire, which is the resistance under fire conditions. We have seen how to calculate resistance of steel members when they are subjected to fire. And then we also had a discussion which says that the cold condition demand or the structural demand on a structure when fire is not there, okay, that is generally greater or equal to the demand under fire conditions. Several building codes specify the partial load factors for fire limit states, okay, and the main thing to notice here is that for live loads, okay, so for permanent live loads and variable live loads, the factors are generally lesser. The basic idea behind this is that during a fire, a lot of combustible items begin to burn, and hence their mass, which was acting on the structure earlier, is no longer there. Hence the overall load reduces. Okay. So the design under fire scenario, these entails these following things. One is reduction in load demand. This reduction is happening because combustible items are getting burnt away. Also, people who were maybe living in the building, they would have been evacuated before the time the fire intensifies. And after the fire intensifies, which is the post flashover stage, that is when it becomes important from a structural point of view. Then there will be additional internal stresses or strains due to thermal effects. So we saw that a member can expand, and if it is restrained, this expansion leads to additional stresses. These additional stresses may cause yielding as well as they may cause buckling. For non-uniform exposure, it can cause thermal bowing or curvature due to thermal effects. Then we saw that generally the strength of materials reduces with increase in temperature. We have seen this in detail for steel structures. In this lecture, we will consider concrete as a material, and we will see how material properties of concrete change with temperature. And one very important aspect for RCC structures is that there can be a reduction in cross-sectional areas. Okay. And this predominantly happens due to spalling. So, if we have an initial cross-section of a beam like this, say this is exposed to fire on 3 sides, okay, which is a typical fire exposure condition for beams, then some parts of the concrete which are exposed, okay, they may spall. What I mean by spalling is that chunks of concrete can fall away. And why does this happen? This happens due to pore pressure. So any concrete has some amount of moisture content within it, which at room temperature remains in liquid form, okay, whether it is physically attached water or whether it is chemically attached water. At higher temperatures of greater than 100 degrees Celsius, which is typically the case for fire situations, this liquid water becomes vapor and expands significantly, or rather tries to expand significantly. And because of this expansion, it exerts tensile stresses within concrete, and concrete, being weak in tension, can then undergo these tensile cracking, okay, and then fragments of concrete can spall off. So this is where reduction of cross section can happen for concrete structures. And we've already seen that modes of failure can change. A structural member which was not prone to buckling before fire may become prone to buckling because the critical buckling load will reduce, right? Because it depends on E, which is the Young's modulus. This E gets multiplied by Ke, the reduction factor of the Young's modulus. All right, so let's move on to material properties of concrete. First, we are looking at concrete under compression, because compression is the main load carrying capacity component which comes from concrete. Okay. So this particular table is coming from the Eurocode. On the first column here, this is the concrete temperature. Okay. And then as of now, the two columns we will look at is the second column and the fifth column. Okay. So this is a ratio of Fc theta divided by Fck. Now Fck, as you already know, is the characteristic strength of concrete, and Fc theta is the strength at a temperature theta. Okay. So what we are implying is that Fck, when we say characteristic strength, this is at room temperature, or depending on the lab conditions, generally say consider to be 20 degrees or 25 degrees. Okay. The other differentiating factor is the nature of aggregates. Okay. So this particular set of columns is for siliceous aggregates, and this particular column is for calcareous aggregates. Okay. Siliceous aggregates, as you would know, is silica based. So this has mostly SiO2. Okay. Some examples of stones whose crushed fragments become siliceous aggregates can be quartz or granite. Calcareous aggregates are based on calcium carbonate, okay, and calcite being an ore of calcium carbonate, and a very common aggregate which is used and is a calcareous aggregate is limestone, or rather fragments of limestone. So what we will notice is that up to 100 degrees there is no change in the strength. So the strength factor is 1 for both cases, which means siliceous aggregates and calcareous aggregates, both kinds of concrete do not lose their strength up to 100 degrees. Okay. And 100 degrees, if you would recall, is the boiling point of water, beyond which some chemical effects begin to manifest. For example, some of the water will evaporate. Okay. So the gels, the CSH gels within concrete, they will become dehydrated, and eventually some of them will begin to degrade. Okay. And we also know that concrete has some calcium carbonate itself, which forms due to the effects of environmental CO2. Okay. That would begin to disintegrate or decompose around 600 degrees Celsius. Okay. So calcium carbonate would begin to decompose, but up to 100 degrees there is no change. Now from 100 to 500 degrees Celsius change, okay, we will notice that siliceous aggregates drop from 0.95 to 0.6, which means the strength becomes 60% of its original strength, whereas calcareous aggregate concrete drops from 0.97 to 0.74. Okay. So siliceous aggregate concretes, calcareous aggregate concretes. Okay. So calcareous aggregate concretes perform better. And what do I mean by perform better? That their residual strength at high temperature is greater. Okay. So in siliceous aggregates it is only 60%, calcareous aggregates it is about 74%. Now in both cases, beyond 500 we will see that siliceous aggregate goes to less than 50% strength, calcareous aggregates is still about 60%. Okay. So if we have to formulate a common design strategy for concrete structures in general, we may like to choose this 500 degrees Celsius as some kind of a threshold, because around 500 both concretes lose approximately half of their strength. Okay. Now this table has two other columns. Okay. These are giving strains. So these will become useful when we are interested in the stress strain graph of concrete. Okay. For the design calculations and methods that we are learning, as of now it is not required for us. But if one wants to do advanced calculations with respect to concrete structures, then these values of strains are also important. Now, concrete, although it has very low strength in tension, but it still has some strength. So again, generally for most of the design, we do not consider the tensile strength of concrete. However, if it is necessary in any application, the Eurocode also gives the variation of the ratio of tensile strength. Okay, so this K C T is the ratio of concrete tensile strength at sorry at temperature theta divided by the concrete tensile strength at say 20 degrees Celsius or room temperature. Okay, here also you will notice that up to 100 degrees there is no change in strength, and this is all predominantly governed by evaporation of water. After 100 degrees there is a linear decay. Okay. Obviously experimental data will be above and below this, but this is a general regression line. Okay. And if we were to draw a line at 50, which is 50% of the strength, we will see that around less than 400 degrees, the tensile strength reduces by more than 50%. Okay. So for this reason, spalling can initiate even in the early stages of temperature exposure, okay, because the tensile strength is dropping very fast. Okay. So even though the concrete may continue to carry load, the tensile zone spalling can begin much before 400 degrees Celsius. So this is a graphical representation of both these strengths. So the graph on the yellow here, this is for calcareous aggregate concrete. Okay. Graph on the red here, this is siliceous aggregate concrete, and graph in blue here is the tensile strength. So we see that the tensile strength drops much quicker as compared to both the compressive strengths, and the compressive strength in case of siliceous aggregates drops faster compared to the calcareous aggregates, something we have seen earlier also. So if we draw a line here which is at 500 degrees, we can read out several things. This is the strength of siliceous aggregate concrete around 60%, strength of calcareous aggregate concrete around 74%, which is the value given in the table. Okay. And strength in tension is only about 20%. Okay. So this is where spalling can begin to happen much faster. These are some photographs which show the concrete cubes at different temperatures. Okay. So we casted this 150 mm concrete cube, the standard concrete cubes, exposed them to different temperatures in a furnace, and then removed them out of the furnace, allowed them to cool, and then took these photographs. Okay. So this lowest image is for 150 degrees Celsius. You will see that there is not much discoloration that has happened, and the last image here is at 900 degrees Celsius exposure. You will see discoloration as well as a lot of micro cracks which have formed. Okay. And expanded photograph is shown here where we see very elaborate cracking patterns indicating almost zero strength in concrete at this point in time. So if you go to 900 degrees here, okay, so we see that the strength of concrete available at that point in time is about 15% only. Okay. So for that reason, it is practically entirely gone. Okay. Intermediate temperatures are shown here, and some slight discoloration can be seen, although the discoloration itself is not a very reliable metric to infer what temperature the concrete would have seen if you are doing a post fire analysis. Okay. An analysis from a strength point of view or from the X-ray diffraction point of view, which gives out which minerals are available, which minerals are not available, those kind of metrics are better. Those were the mechanical properties. Then for Wickstrom's method for thermal calculations, we also need thermal properties of concrete. Okay, and since water is present in concrete even after curing, the water content plays an important role in its specific heat. Okay. So the blue curve, which is this, which corresponds to U equal to 0, here U is the water content in percentage. So for 0% water, which is purely dry concrete, okay, the specific heat is generally low. U equal to 1, which is 1%. Okay, so specific heat here is greater, but then around 200 degrees it comes back to the original curve or to the dry concrete curve. Similar is the story for U is equal to 2% and U is equal to 3%. As we can see that the greater the amount of water, the larger is this peak here. And all of this is happening between 100 to 200 degrees Celsius. Okay. So up to 100 degrees Celsius, not much change. This is where water begins to evaporate. Okay. And when it evaporates, it absorbs more heat. So that is where the specific heat itself goes up. Now from a modeling point of view, this particular zone may or may not be modeled depending on the applications, because if we see the strength curve, up to 100 degrees there was no change in strength, and up to 200 degrees also there is not much change. Okay, so 200 degrees is still almost 97%, 95%. Okay, so oftentimes it is possible to take a constant specific heat for concrete when we are doing thermal modeling, because it simplifies the analysis process. Unlike steel, in concrete, the density also becomes a function of temperature. Okay? As we know that concrete is composed of multiple materials, all of them decay or decompose or vaporize at different temperatures. Okay? And that is the reason the density will reduce as a function of temperature. Okay? So in this zone, which is 100 to 200, water will evaporate, CSH gel begins to decompose. Okay, CSH decomposes quite a bit. Then there is CaCO3 or calcium carbonate decomposition which happens. Okay, and that basically continues. So if you are trying to model again heat transfer more accurately, it is better to consider the density reduction factor. Okay? And the reduction factors are always defined in a similar manner. So if you are calling this as K rho, this is density at a temperature theta divided by density at 20 degrees Celsius. One thing more you will notice is that the drop is also not extremely high, only about 12% to 1200 degrees. So if you are looking at say up to 1000 degree temperature, okay, so the drop in density is only about 10%. So this can be modeled or can be left out depending on the choice of designer. Then we have thermal conductivity. Thermal conductivity generally is seen as two things, a lower bound and an upper bound, and this also happens because there is a wide experimental spread around this. Okay, so a lot of experiments done. The conductivity of concrete depends a lot on its composition, okay? And it is especially true for lower temperatures when a lot of thermal decomposition and vaporization has not happened. The variability is higher, whereas when we go to higher temperatures, okay, the leftover materials are more standardized or similar, so the thermal conductivity becomes more harmonized. And in any case, the overall range is somewhere from 1.9 to 0.5 watt per meter Kelvin. these were the properties of concrete. But all concrete structures are reinforced generally with steel. So we have to discuss material properties of reinforcing steel also. So in reinforcing steel, mainly the parameter we worry about is strength. So here we have two graphs. This is again coming from the Eurocodes. Okay. So the graph in blue is what is of interest for reinforcing concrete, whereas the graph in the orange, this is for pre-stressing steel. Okay. Now in reinforcing steel, we will see that up to around 350, 380 degrees, there is no change in strength. The reduction factor remains 1. Okay. And again, we will say that this reduction factor ky theta is Fy theta, which is yield strength of the reinforcement at a temperature theta divided by Fy at 20 degrees Celsius, which is the room temperature yield strength. Okay. Now from this to up to around 650 degrees, it drops quite significantly to become 10%. Okay. And after that there is practically no strength. Now again, we can look at the temperature at which reinforcement loses half of its strength. Okay, so that is a number which is around 550 or 520 degrees Celsius. If we compare this reinforcing steel strength with structural steel strength, okay, so structural steel is mild steel, which is used for fabricated steel structures. Reinforcing steel is typically thermomechanically treated, or HYST bars. Okay, so from a chemical composition point of view, these are different. So this graph on the left, this we had seen earlier in design of steel structures, okay, where this yield strength factor, reduction factor, there was no change up to 400 degrees Celsius. Okay, and after that there was a drop. In reinforcing steel, the no change temperature is less than 400, not 400. Okay, so this is a slight change. However, the nature of this graph, these two drops are similar in nature. Now with materials properties discussed, we can talk about the assumptions in thermal analysis for RCC structures. Okay. We have already discussed in a previous lecture that a semi-infinite type idealization can be used for concrete, okay, which means that temperature on the surface is something, but temperature away from the surface is not affected by the temperature on the surface. Okay, and one can calculate penetration depth, that how much deep it goes in how much amount of time. Then using these ideas, Wickstrom's method was developed, which enables us to calculate temperatures of insulating materials, or in this case reinforced concrete materials for structures, when they are exposed to the ISO 834 graph. Okay. So ISO 834 graph is the time temperature standard curve, which is used to determine fire rating of different systems. It can be strength fire rating, insulation rating, or integrity rating. Okay. And similarly for steel, for rebars which are steel members, we can consider a lumped capacity. Okay. And in addition, what this allows us to do for reinforced concrete is that whatever is the temperature around this bar, we can say the bar also is of the same temperature. Okay. So all the reinforcement bars are at the same temperature as the surrounding concrete. So practically, for the purpose of thermal analysis, we do not need to model any rebars. So there is no need to model reinforcing steel separately in thermal analysis. This particular idea significantly eases the thermal analysis. Okay. So all we have to worry about is the overall geometry and shape of the concrete part. If we have to worry about reinforcement bars, then the complications become quite high, because one, reinforcement bar sizes are small, so the mesh size has to be really small to be able to capture anything here. And then this is a very simplified case. In reality, there will be bars on the compression side, there will be stirrups and all of that. So modeling all of this becomes very challenging. So this is where, for thermal analysis, we are able to model only the concrete part and we leave out the steel part. This slide shows further assumptions which are there for RCC structural analysis. Okay, so previously we saw assumptions for thermal analysis. So in structural analysis, it is common across different codes that any strength of concrete under tension is ignored. Okay, so we do not take into account, say for beam analysis, any concrete in the tension zone, we say it's not contributing to the overall strength of the structural member. So concrete strength in compression is only that is considered. Okay. Now, when we did a thermal analysis example, we came across this kind of a contour diagram. Okay, so this is a contour of temperatures, say at 1 hour exposure. Okay, we did only the left half of the beam, because when this is exposed to fire on 3 sides, okay, there is a line of symmetry at the center, which means we can model only the left half and take a mirror image for the second half. In the same section, we will have rebars. Say they are located, let's say like this. This is for the compression, and say this is for the tension. Okay, there will also be stirrups. Now, in the previous slide, we said we can assume the rebar temperature to be same as that of the concrete temperature. Okay. So what it means is, obviously we need to calculate rebar temperatures, right? Because we have to consider the strength degradation. So K, Y, theta of rebars we do need to consider in design. How do we get that? We can just get the coordinate location of where the rebar's centroid is, okay, and from this temperature contour, which is for the concrete section, we read out the temperature. Okay, so that gives, for say ith bar, we can get the rebar temperature directly from the contour, and the contour of temperature distribution in concrete. Okay, so we have done the calculation of temperature without considering any rebars. Then we draw the contours, and from the contours we read out the temperature at the coordinates where the centroid of the rebar is located, and that becomes temperature of the rebar. Based on that temperature, we can find out the reduction strength factor, okay, and that reduction strength factor is eventually considered for design. Now, when we were discussing the temperature based properties for concrete, we saw that 500 degrees Celsius was a temperature which was important from the point of view that for most concretes below 500 degrees, we can say half of its strength is gone. All right. So from there, a simplified design methodology comes in. Now this one is called 500 degree isotherm idealization, and this is one of the key ideas in Eurocode. Okay. So if say we do not use this idealization, what would be required is that we go with this entire contour, okay, and let us say this is the neutral axis here. Okay, so the concrete below, obviously it's in tension, so we do not consider the strength. But in compression, what we'll have to do is that this part of the concrete is at a certain temperature, so we take that strength, this part of the concrete is at a certain other temperature. Okay, so then for this strip we take that, okay, and likewise. So for the next we do that. Okay, so in such a situation we need to then consider this F's K C theta versus temperature, which is strength reduction factor of concrete compressive strength with respect to temperature. Okay, and for each strip we would need that temperature and strength reduction factor, and the compressive strength of concrete has to be scaled in accordance with the strength reduction factor. So that would significantly complicate the calculations, although it can be done from the basic principles of mechanics of solids, but it does complicate calculations quite a bit. So from that point of view, this 500 isotherm idealization is a very useful idealization. Okay, let's look at it. So it postulates two very easy to use stipulations. First one is that concrete within the 500 degrees Celsius isotherm, okay, we should say here isotherm, that remains unaffected, which means it has full strength, whereas concrete outside the 500 degree isotherm has zero strength, which means it is to be ignored, right? So let's look at it from an illustration point of view. So say this is the thermal analysis that we are doing. Okay, this gives us contours of temperature. Okay, these are contours. From these contours we pick the contour where temperature is 500 degrees. Okay, so this is the 500 degrees Celsius isotherm, and you may recall that isotherm means a line on which temperature is same. Okay, so what this method says is that concrete inside the 500 isotherm, this has full strength, and concrete outside the 500 isotherm, this has no strength. Okay, so this is a very simple sort of assumption or approximation that has been also compared from a lot of experimental data. Okay, and especially for beams it has been found to be very accurate. So it enables us to bypass a lot of complicated calculations, and we are able to use this for analysis, and we will see how we use this for analysis. Okay. So the illustrations shown here, this is an example of a beam. Okay. So when we draw this red curve, this is the 500 degree isotherm. Okay. So this is the new location of effective concrete. Okay. Obviously there will be a neutral axis also. What we are saying is the effective concrete under this situation is this. So in the compression zone only, this is the effective concrete, and here strength remains FCK without any reduction, right? The outside concrete, this has zero strength. Okay, so which means as if the boundary has come back. However, I would like to note that although it has zero strength, for thermal analysis purpose, we do not change the boundaries, which means for thermal analysis this outer boundary still remains for the purpose of thermal analysis. Okay, but only from structural analysis point of view, this is the effective section in concrete compression. Okay. So, if the original width of the beam was B, okay, there is a new width now, which is this, which is called B fire, okay, and B fire is simply B minus, say, this distance plus this distance, okay. And since this is a 500 isotherm, okay, if we say that uh, the horizontal direction is x axis, this distance here can be called as x 500, or the x coordinate of the 500-degree isotherm, okay. So, this x 500 gets reduced from both the sides, okay. So, B fire is B minus 2 times x 500. Okay. This is how this idealization helps us in doing this. We will talk about this D fire when we do examples, but the general idea is that there is a D which is under cold conditions, okay, which is the distance from the compression fiber to the centroid of the rebars, okay. But as these bars get heated up and their strength changes, this D can change because the centroid of the rebars themselves can change. Okay. Now, a similar sort of concept, so this particular thing that we have seen is for a beam which is exposed to 3 sides on fire. A similar concept can be seen for columns, okay, where let us say if a column is exposed on all 4 sides, this is the nature of the 500-degree isotherm method. And just like in case of beams, we will define a B fire and an H fire or a D fire, whatever you want to you are calling, okay. And idea remains the same, that concrete inside this 500 isotherm, this has full strength FCK. Concrete outside is not effective, 0 strength. Okay, so this is 0 strength. Right. So this is 0 strength, and for rebars, we take the temperature from the concrete only thermal analysis, and we subsequently use the strength reduction factors. Now, these are requiring 2-dimensional heat analysis because there is a 3-sided or a 4-sided exposure. However, we can also consider a slab, which has, let us say, these are the reinforcements. So, a structure like a slab component will be exposed to fire either from below or the above, but generally only from one side. Okay. So, because it is only from one side, the heat transfer problem here becomes one-dimensional. Okay. So, here we have 1D heat transfer, and hence the 500 isotherm will be parallel to the distribution reinforcement like that. So, the effective concrete remains like this and the ineffective concrete is below. So, since this is a one-dimensional heat transfer, generally the 500 isotherm will not go above the neutral axis in this case. So, generally it does not affect the analysis as much, except for the fact that for only rebars we need to consider the temperature effects. Now, let us look at design of beams. Okay. So, again, before we go to the fire design, we will quickly review the section behavior in flexure. Okay. So, what we have here is a section. Okay. So, for a moment, let us say this is not B fire, this is only B. So, the original width of the beam is there and original depth of the beam is there, capital D. We define a distance small a, which is from the bottommost fiber to the centroid of the rebars. Okay. So, centroid of the tension rebars is given here, that is this distance small a. Then from the topmost compression fiber or from the compression fiber, we define a distance small d. Okay. This small d is the effective depth, and effective depth we know is that small d is capital D minus A. Then we also define x, okay, which is the depth of neutral axis. So, x is depth of neutral axis, which is usually calculated when we equate the compression forces to the tension forces within the section. Okay. Now, one of the simplifications which helps us in fire design calculations is the stress block of the concrete in compression. So, in IS 456, you would recall that stress block of concrete is generally taken as this parabolic shape, right. So, where this is 0.45 FCK, okay, then we have 4 by 7, 3 by 7 and like that. So, this part is constant, here it is parabolic. But since we saw that when we consider the 500 isotherm method, some part of the concrete here will be gone, okay, and if it is a 4-sided exposure in case of a column, then like this it will be gone. So, this parabolic stress block again becomes more challenging from a computation point of view. And even with all of this, IS 456 also states that even though this parabolic curve is what is given there, but one can use a trapezoidal or a rectangular or any equivalent shape for the stress block as long as the effects are considered properly. Okay. So, for the purpose of this lecture, we will use a rectangular stress block which is defined, okay, and these definitions we are taking from the Eurocode, where the stress block's vertical extent is obtained by multiplying the neutral axis depth with lambda, okay, so that is this, and the strength extent is taken by multiplying FCK with eta. Eta and lambda, these are two parameters that we will see. What this allows is that this Z, which is lever arm, its calculation becomes more straightforward because D becomes simpler, okay. And this force which is acting here, which is the compressive force, okay. So, the compressive force magnitude will be width, which is this, multiplied by times the area of this stress block, which is eta times FCK multiplied by lambda x, okay. And the location of its action will be at a distance lambda x by 2 from the top, because this is a rectangular block. So, centroid is simple. So, then that simplifies calculation of Z, okay. So, Z becomes D minus lambda x by 2, right. So, this is D, the total depth, effective depth, and minus x by 2. And we will see later that as the temperature increases, this A will change if there are multiple layers of reinforcement. When A changes, this small d also changes, and when small d changes, this Z also changes, and hence the moment also changes. So, this is MU1, which is for the balanced section. Due to reinforcing steel in the compression zone, there will be an MU2, which is simply balancing the compression steel compressive force and the remaining tensile force from the tensile steel, and this Z dash is more straightforward. So, generally this distance is defined as D dash. So, Z dash is simply D minus D dash. Now, here we see the values of these parameters lambda and eta, okay. So, these are defined in the Eurocode. So, the value of lambda, which is the vertical extent of this stress block, is 0.8 minus FCK minus 50 by 200, okay, but the value has to be less or equal to 0.8. So, what it means is that for any FCK, which is less than 50, this term is not there. So for FCK less than 50 MPa, lambda is equal to 0.8. When it is greater than 50, then this begins to reduce it further from 0.8. Similarly for eta, it is 1 minus this with the maximum value of 1. So again for FCK less than 50 MPa, okay, the value of eta is 1. Okay. When FCK is greater than 50, then this begins to reduce eta. Okay, so we can say eta versus FCK, there is a value 50 up to which it is 1, and then it reduces linearly. Similarly, there can be, you can visualize it for lambda. Right? So there is lambda versus FCK, there is a value 50 up to which it is 1, and then it reduces gradually in this slope. Once we have defined all of these, okay, then we can calculate this moment mu1 and mu2. So again, mu1 is the balanced section moment, okay, and so mu1 can be calculated as ASD times FSD fire. Okay, so FSD fire is the reduced strength, okay, multiplied by Z, which is the lever arm. Okay, AS1 is the total area of steel in tension, which corresponds to the balanced section. And mu2 can be similarly calculated as ASD2 times FSD fire. Okay, this is again the reduced average strength of all the tension reinforcement, which correspond to the compression side reinforcement. Okay. And this also has to be equal to this FSCD fire, which is here, because the temperature here can also be more than 400 degrees, which is when the strength begins to reduce. Okay, so we consider the rebar strength appropriately for compression steel as well as for tension steel and do the calculations accordingly. So as we were discussing, this FSD fire and FSCD fire, they depend on the strength reduction factor of reinforcing steel, which is the blue curve here. So there are two ways in which we can calculate this. Okay, so remember that we have a section and we can have, say, multiple layers of steel here. Okay, so one is that for the section we calculate the temperature at the centroid of each rebar from the concrete thermal analysis. Okay, that we designate as Ti, which is temperature of ith bar. Okay, and from there we calculate average temperature of all the bars. Okay, so for all of them there is a T average. Okay, for all of these there is another T average. So this is for compression bars, this is for tension bars. Okay, and using this T average, from here we calculate the average reduction factor. So one way to define is like this. So the reduced strength is this average factor multiplied to the original strength, and same thing we can write for the compression side. So FSCD fire is KY average for compression multiplied to FSCD. Okay. However, there can be a more accurate way of calculating this, which is that now if we consider the ith bar, okay, so let's say AI is the area of this bar, FSD comma I, this is the strength, cold strength, and KSI, this is the reduction factor of ith bar. So then we can define an area weighted total strength, which is defined like this. So FSD fire is summation I equal to 1 to n. So we sum up the K times FSD plus times AI. So this is the overall reduced force summation for all the bars, and divide that by area of all the bars. Okay, so that gives the average, again a different kind of average, but average FSD fire. Okay, so this is more accurate and not very difficult to calculate either. So generally this is a better choice. Okay. Same thing can be done for FSD fire, which is FSCD, okay, which is if you have bars on the compression side. So there again we can calculate area, strength, etc. for everything. Now this cold strength generally will be same. Okay, so this will go out of the summation, but area of bars can be different, which is where this more accurate method is better. Okay. And finally, this rebar centroid we have been talking about, right? So rebar centroid is the distance from the bottom fiber to the centroid of the rebar layer. Okay. And this is required because we define the effective depth as capital D minus A. Okay. Now this A is a centroid. If materials have the same strength, then the centroid can be seen as the geometrical center line. Okay. However, because each of these rebars can have different area and also different temperature, so different strength, hence the overall centroid may change. Okay. Now the overall centroid for a single layer of reinforcement will not change, okay, because all of them are anyway sharing the same centroid. But let's say if we have multiple layers, so then the lower set of bars will be at a higher temperature. So these will be at a higher temperature, and the upper set of bars will be at a lower temperature. Okay, so in such a case, for cold conditions, A is generally this. However, and under higher temperature conditions, this A may increase. Okay, so we will need an A fire, and that is what this A fire is. This is a weighted average. And once we have A fire, then we can define D fire as capital D minus A fire. Okay. So that is what is this D fire will be. Okay. So now using this B fire and D fire, we will be able to do section analysis, and we will be able to calculate the moment capacity of a RCC beam at high temperatures.